Good morning, everyone. My name is Sheng Yan. I'm lecturer in the High Performance Network Group in the University of Bristol. Today, I'm very happy to have the opportunity to present our work about programmable ROADM for SDM WDM networks. Here, I would like to acknowledge the contributions from my colleagues Richie Young and Li Liu to this work, and this work is supported by Token Project. Here is the outline of my today's talk. Firstly, I will give a brief introduction about SDM technologies. I will discuss the several key considerations of ROADM design in multiple fiber-based optic networks. In the second part, I will present our design of the programmable ROADM system for SDM WDM networks. In the third part will follow and simulation and discussion. And the last part, I will conclude this talk. So here is a figure shows the development of optical capacities, and we have witnessed several key innovations in optical networks. For example, there is WDM optical amplifications and the recent digital coherent detection technologies that's using advanced modulation format. And we have noticed with this development, we are quite close to the physical limit of the single mode fiber. And to further increase capacity, and we require new technologies. And space division multiplexing technology provide actual dimension and to transfer the information. And so they provide a potential solution to further increase optical bandwidth. So there are several technology can be used to achieve space division multiplexing. And firstly, is uncoupled solutions. And for example, we can put multiple single mode fiber together and a bundle, or we can use multiple fibers. And so this is uncoupled solution. This is a 32 core multiple fibers. Or we can use the strong coupled solutions. So for example, multiple fiber with a core coupling between each cores and multi-mode fiber. Or we can combine multi-core and multi-mode to achieve more high capacity. For example, here show 19-core 6-mode fibers. But all these solutions may target for the transmission and to deploy the SDM technology in optic networks. Another thing we need to consider about is switching. And if we go look into the different technologies, we see the strong coupled solution. They require complex MIMO processing to separate or decouple different space mode or different cores. And this will make the intermediate switching impractical or impossible. So in here, we believe the multiple fiber will be the good solution for the deploy SDM technology into optic networks. And why? There are several key considerations. And firstly, the current uncoupled multiple fiber provide flexible core management. We have seen matured fan-in, fan-out device, and they doesn't require high complex MIMO. That means in the 18 node, we can implement the switching node. And secondly, we notice their key component have been available. For example, multi-core EDFAs, that's for transmission environment. And we also see some recent transmission environments have demonstrated the capability using multi-core fiber to achieve high data rate and long distance transmission. And still, so how about the switching? And because we're using the uncoupled multi-core fibers, we can treat each core as a single mode fiber. And in the traditional WDM network, we're using WSS to have this routing and select ROADM to do the switching. And if we treat each core and single mode fiber, the question is, can we scale up this design to support support multi-core fiber-based SDM networks? So in that case, we will require a multi-core breakout to separate the microfiber to different single mode fibers, and we can do the similar things to design the routing and selecting ROADM. That is straightforward consideration. But the key challenging to scale up first thing is not practical, because to do this, if we treat each core as single mode fiber, we will require a huge port count WSS for the ROADM, and the port count should be large than degree times the core number. So this is make this kind of huge port count WSS impractical. Second thing, we think this scale up is unnecessary, because with the microfiber with more cores inside, we have seen the core number exceed node degrees. So the full flexible switching is not a necessity. And we also notice that full flex switching will require a very advanced routing algorithm to avoid further spectrum fragmentations. And if this is not practical, unnecessary, so another alternate solution is to provide traffic aggregation. So they can be aggregated to the core or to the super channel, either in space or spectrum. Or we talk about SDM over WDM with hierarchy network. And so our solution is to introduce fiber core bypassing. And we have produced this concept in 2017. And what's the key innovation of the fiber? What the key concept of the fiber core bypassing is that here I show a network connect with 7 core microfibers and with different nodes A, B, C, D, E, and F. And for different node, we can set up a directly point-to-point connection without going through to the WDM switching, and by connecting the core directly at the node. Similarly, we can choose another bypass core, and from node A to node E, or node B to node D, or others. So all these cores in node C, we notice they are using for bypassing. They doesn't require any spectrum switching. The other cores, if they need spectrum switching, and we can using traditional ROADM to achieve the switch. So in this design, I think the massive network capacity do make core bypassing good solution. They reduce the required ROADM degree significantly. And the ROADM degree, if you treat each core as a single mode fiber, so it's how many core they require WDM switching. And also, because they introduce this fiber core bypass direct connection from different node, we actually change the topology. So we can generate different watch topologies. And to make this work, the casing, we need it to be reconfigurable. They're not two different independent networks. They need to be reconfigurable. The reconfigurability of the fiber core bypassing, they enable the compatibility with the current single mode fiber based networks, because we treat each core as single mode fiber. So these microfiber can be integrated with current single mode fiber based networks. And also this reconfigurability makes this fiber core bypassing can be adaptable to traffic changes. So this is a very important. So with this concept, so if you look into the network level and we see a network, for example, here I show a 4-node ring topology network, and we can do this fiber core bypassing. So that means we can provide direct connection from node A to node D and node B to node C. So the ring topology now turn to a mesh topology. And also, you will notice the link are using different sake of the line to connect them, because the link capacity can be adaptable based on how many core you are allocated, how many bypass core have been allocated to this direct connection. So this is in the network level. And if you see in the node level how we achieve this, and this is one node with 2 microfiber in and 2 microfiber out. We only draw one direction. Actually, they can do the both direction, but they show one direction. So we can set up, we're using, we can set up the core-to-core direct connection, and this is for bypass link. And for the other cores, they require WDM switching, and we can using a traditional ROADM architecture. For here is the routing and selecting architecture to do the switching operation. So with more allocated more code to bypass mode, and we can reduce the ROADM scale by introducing programmable bypass configuration. We do reduce the scale of the ROADM, and also this because all these links can be reconfigurable. That means we are provide a smooth deployment with the full compatibility of the current WDM networks, and the current single mode fiber link can be treated as same as the core, so we can provide this flexibility. So this is per node, and to achieve this design from network level to node level, and to achieve the design, and what's the key technology we require? Firstly, we will require reconfigurable core interconnection. So we're using the concept developed by our group, architecture on demand, to manage the core. So you see here, and the fiber input and fiber out using this large port count fiber switch can set up direct connections and between the different fibers and to connect core to core directly, and other core, and we can using a traditional ROADM, and they can be because this architecture we can change or allocate different core to the ROADM, and for the ROADM part we can using traditional ROADM modules to do that, or we can synthesize the ROADM based on the scale. This is based on the architecture demand concept. And because the reconfigurability, we mentioned that reconfigurability is very important. So the reconfigurability will require dynamic optical power management, and also the system level bypass design. We need to set up a bypass link in network level, and to achieve the best performance. So, and to validate the design, and we design the simulation. And here is the simulation setup. And we set up a 6-node topology with multiple fiber links. And each multiple fibers have 13 cores. And so here, the 13 core is more than degree. So we can allocate the bypass link. And for the traffic, we're using the elastic spectrum allocation, and minimum bandwidth 12.5 gigahertz, and we can allocate the different slots for high capacity. And in here, we assume the bidirectional traffic. And the bypass reconfiguration can help to generate different word topologies. The word topology, and so we actually simulate 3 topologies by reconfiguring the bypass cores, and all the baseline is based on the full flexible topology with ROADM without any bypassing core. Here we show the different word topologies by configure different bypass cores. And in topology 1, for each node, we only allocate 1 hop bypass core and 1 2-hop bypass core. And in topology 2, we will assign each node have 2 1-hop bypass core or 1 2-hop and 1 2-hop bypass cores. In topology 3, each node we only assign 2 1-hop bypass core. And so these 3 different topologies. And we generate a different kind of traffic and to validate the design by comparison with full flex topologies. And so you see here, the blank line is show the full flexible topology, and other 3 lines is the different topologies. And we introduce in the bypass cores. And we see there is a slightly degradation of the performance, but this is performance is acceptable range, considering we provide more bypass cores. And with a different kind of traffic, we see the similar situation. And this is, but the different topology we use may have different performance, and that is related to the traffic. So that means the traffic or the topology can be optimized further based on the traffic. So this is the simulation about performance. And also we look into the hardware requirement. Consider this is only 6-core, 6-node network with 13 core microfibers. And based by comparison the baseline design and in the different topology we mentioned that before, we can reduce the required WSS number from 8% or 13% or 11 or 12% based on different topology. And here we didn't mention the required the WSS port number, but the introduced the bypass core, they reduce more for the requirement for each WSS, how many the ports required. So that is only 6 nodes. If we put this design to a full to a complex network, you will see the reduction of the hardware. And we also notice this design reduce complexity of the routing algorithms, but the further research will be done to show how much the complexity can be reduced in this routing algorithm. And we mention that by introducing bypass core, so each WSS will require less port count, and this is more easier to achieve that low skill ROADM. And for future, if we have more large multi-cores, core numbers of multi-cores, and we can using this technology to further reduce the requirement of the core number of the port count of the WSS. So using the 2-stage for routing and selecting, so the first part and the second part both using 2 stages. And so in this case, our design, the maximum port number depends on the number of the WDM cores. And that means in the microfiber, the maximum port count will be equal to the cores that that's required for WDM switching. And we see the simulation also validated the similar performance and the standard design. And we also validated in the the network topology of the NSF network. And so we will see the performance and the hardware efficient, the bypass and no bypass configuration. We have the performance, the similar performance in this setup. And so this is for further reduce the requirement of the WSS port count. And with this concept, we believe they can be extended to the metro network. And for example, in the ring topology, and we can using a Pure-SDM network without using any WDM switching solution, and using Pure-SDM to achieve for the metro network. And with the core, by reconfigure the core, and we have simulates using the different topology, and we can achieve quite similar performance with a Pure-WDM-based switching solution. And this work has been submitted to ECOC 2020, and to show this concept can be used in the Pure-SDM metro network. So I think here I can conclude my talk, and we have discussed our design of a programmable SDM-WDM ROADM system, and we validated with simulation, and they introduced the dynamic bypass core solution, reduce the scale of the ROADM, and achieve a better hardware utilization. And the SDM-WDM to provide acceptable performance and compared to full spectrum switching solution, and reduce the complexity of a routing algorithm. And also this solution can be further extended to the metro networks to achieve filterless bidirectional metro interconnections. And thank you for your attention. And this is a recent relevant publication submission related to this work. And if you have any query, please send an email to me. And thank you very much.